Every single time you open your laptop or tap on your phone, there is an entire microscopic universe buzzing just beneath the glass, right? Now, most of us just see the surface level, the apps, the interfaces, the shiny icons, but today in this explainer, we're going to dive a bit deeper. We're going to look at the pulse of that machinery. We are examining pathogens of the pulse, the biological architecture of malware. And I promise you, by the time we wrap this up, the fundamental way you conceptualize a computer virus is going to be completely rewritten.
So here's a question to kick things off. Is computer code just math, or is it actually alive? I know, it sounds a bit out there. We're always taught that code is just pure logic, right? Strict mathematical commands executing inside a processor, flipping registers from 0 to 1. But what if we completely shifted our perspective for a minute? What if, instead of viewing malicious code as a mere string of mathematical errors or bad instructions, we actually looked at it as a digital organism? This isn't just some abstract thought experiment, by the way. It is a profound, literal reframing of how cybersecurity actually functions at its absolute most foundational architectural level.
All right, let's get right into Section 1, the digital organism. To really understand this, we need to look at the core metaphor of our analysis. On one side of the equation, we have biological DNA. On the other, digital code. And the scary part? Both of these entities share a core terrifying mission. They exist entirely to replicate and hijack hosts. Just like biological DNA operates to propagate itself basically at all costs, malicious code acts as a digital organism that relentlessly replicates. It doesn't just sit there passively on a server waiting around. It actually has a biological drive written directly into its digital architecture. It wants to survive, it wants to evade detection, using techniques you're probably familiar with like polymorphism and obfuscation, and above all else, it wants to spread.
Moving right along to Section 2, pathogen life cycles.
Now that we understand the organism itself, let's break down the actual mechanics of how these infections spread in the wild. It comes down to 3 steps. Find host, hijack, replicate. It is a strict structural mandate. Think about it. Just as a biological virus absolutely requires the living machinery of your cells to synthesize its proteins, digital pathogens require a host program to execute their logic. A piece of malware cannot simply run in a vacuum. It literally has to inject itself into a legitimate, running process on your machine. Once it hijacks that host architecture, it forces the legitimate program to stop doing its normal, everyday job and starts making it replicate the malware's instructions instead. It completely subverts the host's original purpose. And we see this exact biological life cycle mirrored perfectly in threats you hear about all the time, like worms, Trojans, and fileless malware. Take a worm, for instance. It wriggles through network protocols totally autonomously, actively hunting down vulnerable host environments. Or a Trojan, which relies on a disguise, essentially hijacking your trust to bypass security parameters. But honestly, perhaps the most purely biological threat out there is fileless malware. I mean, think of it like an invisible toxin. Instead of dropping a chunky, malicious executable onto your hard drive where your antivirus is definitely going to spot it, fileless malware lives entirely in your computer's RAM. It uses your system's own built-in tools against you, a tactic called living off the land, to execute its payload. It leaves zero physical trace, operating purely within that volatile memory footprint, which makes it an absolute nightmare to track down. But at the end of the day, they all follow that exact same biological pattern. Find a vulnerability, hijack the environment, and replicate.
Which brings us to Section 3, the Capone infection.
So let's look at a visceral historical anecdote that makes this concept of a locked memory absolutely unforgettable. You've probably heard of the notorious mobster Al Capone. Well, in his later years, he suffered a catastrophic physical decline. Medical history actually shows us that his highly capable criminal mastermind was eventually reduced to that of a 12-year-old. And why? Well, it was because of a late-stage biological infection known as neurosyphilis. This pathogen literally invaded his brain, locking away his memories, his cognitive function, his entire identity. It hijacked the very architecture of his mind and held his mental faculties completely inaccessible. He was still physically present in the room, sure, but the essence of who he was had been locked away by an organism that he just couldn't fight. Now keep that tragic physical reality in your head for just a second. Because we see that exact same pathology in ransomware. Ransomware is quite literally a digital pathogen that locks a system's memory. It does the precise, destructive thing to a computer's architecture that neurosyphilis did to Al Capone's biological memory. It invades the system, scrambles the data using military-grade encryption, and locks away those files and memory banks, rendering the mind of the computer entirely useless. And look, what makes ransomware so devastating is that it doesn't just break the machine. The computer is still powered on, right? The fans are spinning, the lights are blinking, just as Capone was still technically alive, but the architecture is being held hostage. The functional memory is devastatingly locked away from the user, leaving them completely helpless while the machine still breathes. It's a really chilling parallel.
Now let's dive into Section 4, rootkits and neurosyphilis.
We have reached the climax of our mere metaphor here, the absolute deepest, most extreme digital infection possible. As many of you know, the kernel is the deepest core of an operating system. Operating down at ring zero, it acts as the literal central nervous system of your machine. It controls everything: the hardware interactions, the memory allocation, the root security permissions, all of it. If a process has access to the kernel, it has total, unquestioned dominion over the entire system. Understanding this specific architectural privilege level is absolutely vital because the stakes of a compromise here are, well, absolute.
And that is why a rootkit is essentially the neurosyphilis of the digital world. Why? Because of where it chooses to live. A rootkit hides perfectly in the kernel, the absolute core of the operating system. Just as neurosyphilis burrows incredibly deep into the central nervous system in the brain, actively evading the body's standard immune responses, a rootkit burrows into the deepest privilege rings of your computer. It sits entirely beneath the level of your antivirus software. By hooking into system calls, it essentially controls the very tools your computer would normally use to find an infection in the first place. So, when the operating system asks to see a list of running processes, the rootkit simply intercepts that request and lies. It completely hides itself from the results. It is just a masterclass in both biological and digital evasion.
And because a rootkit hides so perfectly in the kernel, it is practically impossible to remove. Once an infection reaches this deepest core, whether we're talking biological like neurosyphilis or digital like a rootkit, the host system is fundamentally altered. You can't simply hit delete on a rootkit because the pathogen now controls the very mechanisms of deletion. It controls what the system sees, what it hears, and what it executes. The foundational trust of the entire machine is broken. And this right here is why understanding the architecture of malware matters so much to us. Because once a pathogen hits that core, the battle is essentially already over. At that point, the only true cure is completely wiping the system and starting over from scratch.
So let's take a step back and look at what we've covered in this explainer. We've seen how malware requires a host process to synthesize its code. We've seen how ransomware locks memory architecture exactly like biological pathogens lock the human mind. And we've seen how rootkits act as the neurosyphilis of the operating system, becoming practically impossible to remove once they hit the core. So I want to leave you with this. If code replicates, hijacks, evades, and infects exactly like DNA, are our digital ecosystems actually alive? It is a pretty eerie thought for sure, but it's one that fundamentally changes how we must view and ultimately protect the pulse of our technology every single day.